Hi everyone. Today what we're going to work our way through is horizontal asymptotes. And similarly to vertical asymptotes, today's going to be a little bit of a tough one. What I want to assure you on is take your time. We're going to slowly walk through some stuff. Today's biggest issue is going to be with fractions. So every time we face some confusion or there's a little bit of doubt as we're working through on some stuff, just stop, take your time, and remember, all we're dealing with are fractions. So we're going to walk through this relatively slowly. We're going to then pick up the pace a little bit, and then we're going to slow down when we see the application. Okay? You find your pace to work through on today, whether that means rewatching something a number of times, but you find your pace as we move through. So you see the title on the left. I've got our hyperbola up, that one that we've examined a number of times, y equals 1 over x. And there's our question in the top right corner. Where do horizontal asymptotes occur? Now, when we take a look at that curve, I hope that we would be pretty good to recognize that it is at y equals 0. What I want to do is I want to follow a similar process to what we did with vertical asymptotes. We're going to zero in on a part of our function, and we're going to take our time, like really take our time, breaking through why that asymptote occurs. So let's jump in and let's focus in on part of that curve. So what we're going to do is we're going to walk through the table of values process that we did before. And we're going to slowly work our way examining why we have that asymptote for our curve y equals 1 over x. So what you see on the screen, you have your equation of your curve in red, and then we've got that gold table of values. I want to inch my way along. So let's imagine that we did the same thing we did before. Let's sub in an x value of 1 into our equation y equals 1 over x. Okay, when we do that, we then get a y value of 1. And again, that's why we have the point at 1, 1. Well, now what we can do is we can slowly allow our x value to get larger. That's where my curve approaches my asymptote. And so if I was to sub in, let's say, an x value of 2, well, then I get 1/2 as my y value, and so I get something like this. And if I allow my x value to get larger and larger, so for instance, I jump to 10, well, maybe that's what causes that x value to be at, that y value to be at 1/10. And we could start to see a process, even though we can't see it on the graph, where if I allowed my x value to be 100, my y value becomes 1/100th. Really small value. However, relatively speaking, 1/100th isn't that small. Not when I could sub in an x value of like 10,000, and now all of a sudden my y coordinate would become 1/10,000th. But even that wouldn't be relatively small if my x value was 1,000,000, and so on and so on. And so, why do we end up having an asymptote there? Well, I'm hoping what we can see, even in that very short table of values, is that as my x value gets bigger and bigger, my y value gets smaller and smaller. Okay? As my x value gets bigger and bigger, my y value gets smaller and smaller. Here becomes the wrinkle, though, and why do we have that asymptote? Well, my asymptote occurs, if we wanted to look at it, at y equals 0. It's along our x-axis. So the equation of that line is y equals 0. Well, why does the line y equals 0 represent an asymptote for that curve? Okay, recall what your asymptote is. It is a line that curve is going to approach but not touch. So, why does my curve approach that value but not touch it? Well, we can see from our table why the curve approaches it. Because as x get bigger and bigger and bigger, the y value gets smaller and smaller and smaller. But why does it never touch that value? Well, for that to be the case, we have to examine the actual equation of that graph in a little more detail. What is the asymptote? It is y equals 0. And I'm hoping we either have like two ways to examine this. At the very least, we could say, well, if y equals 0, then I have this equation, and I could multiply out my x, which then states 0 equals 1. That is a no solution, because that is not a true statement. And so therefore your y value could not equal 0. However, I would hope we would have a better reason for that. What is the only way that you can make a fraction equal to 0? It's if the top equals 0. And will the top of that fraction ever equal 0? No. Why? Because it's a constant. It's always 1. And so if we examine the actual curve, the equation of that curve, we notice that our y value could never equal 0. Now, that's not a case that should surprise us. I'm going to put a quick sketch down. That doesn't mean asymptote. Like, you've dealt with parabolas, for instance, that look something like that, and maybe their y value never reaches a value of like -4. Well, that doesn't mean that it's an asymptote. But if you tie together the two features of what we just found, first off, look at your table of values. As your x value gets bigger and bigger and bigger, your y value gets smaller and smaller and smaller. So notice that the y coordinates are approaching a value of 0. But do we ever get to 0? No. Why? Look at the equation. The only way to equal 0 is if the top equals 0, and that will never occur. Those two ideas come together to form the basis for why we have an asymptote as that curve goes forever to the right. And what I want to do now is maybe make that a little bit more formal for us as we proceed. So let's look at a really basic piece of theory, and we're going to run with this basic piece of theory, and we're going to use it to do some pretty good stuff. What you see on your screen now, and I'm going to give you a moment to get that down because I think that is so important, like it's worth copying into a note. When a fraction's numerator is constant and its denominator becomes increasingly larger, the fraction's value becomes smaller and smaller, approaching 0. So notice that that is what we had in this situation. We had the equation of the curve being y equals 1 over x. Notice the key components to that. The numerator in that fraction is constant. It's not changing. It's 1. It doesn't matter that it was 1, if it was 10, if it was 1,000,000. It was constant. Notice what happened when we built our table of values. We kept making the denominator bigger and bigger and bigger. And so what did we find in the table? We found that the y coordinate, the fraction's value, became smaller and smaller. And the key term for us, approaching 0. Can it ever equal 0? No, because the top has to equal 0, and my top is a constant that's not 0. And so if we approach the value of 0, then that means that we never get to the value of 0. And therefore we have our horizontal asymptote. So that blue statement is a huge piece of theory, and that's all that we're going to do all of our work with today. So when things get a little difficult, you find them a little confusing, we're drawing some conclusions to some things, and you're struggling to see the connection with that, come back to this blue statement. When the top of the fraction doesn't change, but the bottom keeps getting bigger and bigger and bigger, then the value of that fraction gets really, really small, always getting smaller, approaches a value of 0. Okay, let's jump in and let's do a little bit with this. And so what you see now is just us zeroed back in on that first quadrant branch of our hyperbola. And what we're going to do is we're going to formally examine end behavior. Now, we've used that term before, end behavior. We're just talking about what a graph does to its extremes. So in this case, what we see on the graph is forever to the right. Well, if we need to examine that then what we're going to do is we're going to look at the limit, because we're looking at a repeated table of values, infinitely many substitutions. What are we doing with our x value this time? Well, we're not approaching an x value anymore. That we're actually doing something with the x values. And we're looking at going forever to the right. So we're going to allow x to get bigger and bigger and bigger in the positive direction. Okay, well, what was the equation of our graph? Y equals 1 over x, so there's the expression for it, 1 over x. And what we can do then is we can examine that end behavior. Now, I'm going to write something down that you will never, ever, ever write down in your solution. I'm going to go through that same process we did when we evaluated our limits yesterday. Okay, I'm going to allow x to approach infinity. And we kind of said to ourselves, so close to infinity, you can treat it like it's infinity. Here's the problem. Remember, infinity is not a number. It's an idea. Increasing without bound. And so, I can't sub it in. So, I'm never going to write 1 over infinity. I am never going to write an expression that has infinity written in it in place of an x value. However, that green is what I'm going to consider. So what that says is my top is constant and the bottom increases without bound. So it keeps getting bigger and bigger and bigger. And if you'll notice, what I've put in green, now defined by the blue, that was our blue statement. My top is constant, the bottom becomes increasingly larger. Well, what happens to the value of the overall fraction then? It becomes smaller and smaller and smaller. Approaching what? Approaching 0. What I have in gold is all you will show me. You never show me that green. Now, here's the problem, that when we look at that gold, that says equal to 0. And we know that that never equals 0, because the only way that you can make a fraction equal to 0 is if the top equals 0. My top does not equal 0. And so, how do I now denote that that's not 0? I have to incorporate that bit, that 0 positive or 0 negative, to state that we're talking about something that's a really, really small value, so close to 0 you can almost treat it like it's 0, as long as we know it's not 0. And so, when I examine then, what do I have in that instant? If I am going to be subbing in on my denominator, values going forever to the right, then those are huge positive values. And so, if I look back up into my original equation, I have 1, a positive value on top, that will be divided by a really, really big positive value. Well, a positive divided by a positive is always a positive. And so what I really have then is a positive bit. And there we go. All you would ever have to show me then is the gold. And now let's just take a peek back at our picture so we can interpret it. What does that mean? That means that as we go forever to the right, as x approaches infinity, we are going to get a really small value that is almost 0, but will always be positive. And notice that what we then found was our graph was always a positive bit. So what does that positive bit actually represent then? It actually represents that we are going to have our curve above the asymptote. And you can see that in the red, that our curve will always be a little bit above that asymptote. So what we just did, and all we included there in gold, was us examining end behavior. And we can see how that plays out with our curve. So what I want to do now is I want to hop onto the other side of the curve, because if you notice, our curve does something a little bit different in the other direction. Okay, so now all I've done is I've just zoomed in on the other side of the curve, and we can go through and we can examine the end behavior going forever to the left. So what are we talking about then if we're talking about our x values? Well, then we are addressing as x goes bigger and bigger, that means increasing, but in a negative direction. What was the equation of our curve? 1 over x. So we're going to deal with that same thing. Now what that limit says, and for us to examine going forever to the left, is we are picturing this in our heads. But as I said before, we are never going to sub in infinity or negative infinity into an x value. It's an idea, not a value. So what we are imagining then is the top of my fraction is constant, and the bottom of my fraction increases without bound, except what's different in this case is we are getting to be a huge negative value. So the way you can always look at that is it's a big negative value that's always getting bigger. Okay, well, what happens to a fraction's value where the top is constant and the bottom gets bigger and bigger and bigger? Then my value gets smaller and smaller and smaller, approaching 0. However, we never get to 0 because the only way to get to 0 is if the top equaled 0 and the top of my fraction was 1. Okay, so if it's not really 0, then what is it? Well, on the top of my fraction, I am subbing in, it is a positive value, but on the bottom of my fraction, I am subbing in huge negatives. So when I actually calculate that bit, I'm going to have a positive divided by a negative value, and therefore that 0 isn't really 0, it's really a really small negative value. And so you could imagine going through repeated substitutions in a table of values and subbing in like -10, so now you get -1/10, subbing in -1 million, so you get like -1 millionth, -1 billion, -1 billionth. We keep getting smaller and smaller and smaller, but we will always be a negative value. So how do we interpret that negative then? Well, where are negatives relative 0? They are always below. And notice on your graph, what you have is our red curve, which always exists at a negative value, and it is approaching our asymptote from below. Okay, what we just did was examine our end behavior, and that is going to be a practice that we're going to have to do to find every horizontal asymptote. So let's make sure that we get down that theory in detail. So what you see on the screen right now is something that I think is important for us to get down. What we have in white is how we examine our end behavior. We examine the limit as x approaches negative infinity of f of x and the limit as x approaches positive infinity of f of x. You'll notice that I wrote those in the positions I did. Just as with vertical asymptotes, I think it's important that when you evaluate your limits, put your left side limit, your forever left limit on the left, and your forever right limit on the right. Lastly, you'll see in red, don't forget that what we're always finding is the result of repeated substitutions into a table of values, which means we're always finding the y value of our function. So what is it that the y value is approaching as we go forever left or forever right? Okay. We've gone through a ton of theory now. And what I want to do then is I want to go through and I want to examine a specific case. It's not going to be a straightforward case. We're going to jump into this like both feet. But I want us to be able to see that act in practice. And I think if there's some confusion, and likely there is, we're going to be able to kind of work our way through it in this instance. Okay, here we go. Okay, so the question you see on the screen says, determine the end behavior of the curve. And really, in theory, us finding the end behavior is us establishing that as we go to the extremes in both directions, what is that curve doing? And therefore, if it has an asymptote, what is that value that it is approaching? So we're going to find the end behavior. Okay, one of the ways for us to do that is to examine what is happening as we go forever to the left and forever to the right. However, can I just get you to take a look at the equation in A, and we can maybe see that that's not going to be that easy to examine. Now we're going to try to be picturing like, okay, so what's going to happen when we sub in a really huge negative number on top, add 2 to it, and then 3 times a really negative number on the bottom, subtract 1 to it. I know we're never going to write that, but I want us to maybe see one key feature. Do you notice that even in that form you would never write? You would have to substitute infinity, or that concept, into both the top and the bottom. So that causes us a wrinkle. And maybe we can say that it was relatively easy to examine what happens to the value of a fraction when the top was constant. But in this case, my top has a variable. So how do I go through and evaluate that? Okay, so let's get rid of all this blue stuff over here because I don't think we're ready for that yet. And here's an approach that we can use, and it's just us manipulating that fraction. So we're not going to change its value, we can't do that, but we can change the way it looks. And so if our concern was that we had variables on both the top and the bottom of the fraction, then why don't we just divide out that variable? Now, some of us might say, like, yeah, but I can't divide out the variable because there isn't a variable in every term. And I'm going to argue to you, we don't care. What we're going to do is we're going to divide the top of that fraction by x and divide the bottom of that fraction by x. Now, again, you might look at the top and you go, yeah, but both terms on top don't have an x. And I'm going to argue to you, I don't care. Now, this would be the line that we're actually going through. And I would hope that regardless of the way we see it, we realize that either of those green forms have not changed the value of that fraction. Like notice, even in the original with the old-fashioned division symbol, that would just be what you would consider reducing a fraction, dividing something out of the top and the bottom. So I'm going to eliminate the fractions within fractions, and we should be able to see then that to divide the top means divide all terms. So I'm going to divide x by x and divide the 2 by x. Now, what do I have on the bottom? I have to take my 3x and divide it by x, and I have to take my 1 and divide it by x. Now, you may look at that and say, like, okay, that's really ugly. However, when we examine that, we're going to notice that those x's will divide out, and these x's will divide out. And so that whole expression then is going to simplify down to a 1 plus 2 over x all over a 3 minus 1 over x. And even though we might look at that blue form and say, oh, that's so much uglier than the original function, I'm hoping that we recognize that that blue form is actually really useful to us. We love that blue form. because you'll notice that every fraction that contains, the 2 over x and the 1 over x, are both fractions where the top of that fraction is constant and the bottom of that fraction is a variable. And hopefully we were all good to examine what happens to a fraction where the top is constant and the bottom is a variable as x becomes bigger and bigger. That was that blue statement that we addressed earlier on. So even though 1 plus 2 over x all over 3 minus 1 over x looks a lot uglier than the original function, it is so much more useful when we're examining end behavior. So that approach that we just went through is going to be an approach that you're going to have to tackle many times over. So let's get down this formal process. What you see on the screen is something that you're going to want to get down. At some point during this segment, you're going to want to pause the button because you're going to want to get this down, because unlike a lot of things, like, there actually is a pretty specific algorithm to be able to go through and find horizontal asymptotes. You'll actually see me number them. Like, this is a step 1 do this, step 2 do this. So when you take a look at number 1, that was the act that we just did. We divided all terms by the largest power of x. And what you'll notice is, in that previous function, we had an x on top, we had an x on the bottom, so the largest power of x was x. Had we had x squareds in there, or x cubes, and so on, then we would have to divide by that largest power of x. You'll see in red why we do it. It guarantees that we will always have a constant divided by a variable. And that's our base theory for examining horizontal asymptotes or end behavior. After we've done step 1, well, then we can just finish it off and we can go through and actually examine the end behavior by discussing going forever to the left, forever to the right. We're going to examine the limit as x approaches positive or negative infinity. What are we doing again? You see it in the red. We're just finding the y value that curve is going to approach. Okay, if you don't have that down yet, then pause it. It is that important to get in your notes. What I want to do is I want to go and I want to use that approach now to examine what we had in the previous function, and now to actually follow through on step 2. I want to examine what that end behavior is. Okay, pause it if you need to, otherwise we're moving on. And so, what you'll see there is our original function, and then in blue, we've manipulated it to make it useful. So, in red, what we're going to do is we're going to examine, first off, going forever to the left. What form of that function do I want to use? I want to use the uglier version. That manipulated version. Okay, here we go. We're going to evaluate that limit. So, I need to imagine now that I am subbing in huge negative values for my x. Well, the first thing I notice is on top, I have nowhere to sub it in to my 1. And so if I go to sub in huge x values, then my top is 1. At least with the first term. Now, I want you to hang tight on this one, because this is often what some people will write down. They will then include the plus, and then they examine what happens to this fraction. And so we'll start to then say, okay, well, there's nowhere to sub it in for the 2. And then on the bottom, I have a huge negative value, and in my mind, I'm thinking this. Okay, well, we already know that we're not going to write that down. So, I'm going to get rid of that 2 over negative infinity. And now what I'm just going to focus in on is that circled fraction, 2 over x. Okay, well, anytime that I have a fraction where the top is constant and the bottom gets bigger and bigger and bigger, then that fraction value approaches 0. But I know that it will never equal 0 because the top of that fraction is 2. So it means that I'm going to have 2 of something. I'm going to have a bit. Okay, well, what sign bit is that going to be, positive or negative? Well, my top of my fraction, the 2, is positive. The bottom of my fraction, though, I will be subbing in huge negatives. So if I take my positive value and I divide it by a negative value, that will always give me a negative bit. And then I can go through the same thing on the bottom. So I have nowhere to sub it in for my 3. I'm subtracting. And then my next fraction is 1 over x. Okay. Anytime I have a fraction where the top is constant, the bottom gets bigger and bigger and bigger, then the overall fraction approaches 0. It never equals 0 because that top is 1. So it's 1 of something. It's a tenth, it's a hundredth, it's a millionth, it's a billionth, it's a trillionth, it's 1 of something. Okay, well, what sign is that something? Well, my top is a positive. I'm subbing in huge negative values on the bottom. That's going to give me a negative. Now, at that moment, I want to just take a look at that because I want you to notice that you've actually gone back to like grade 7 and grade 8 in what you wrote down. I just want you to look at the top for a second. Because what that top says is you're going to take 1 and you're going to add to that a negative number. Like it's a negative bit. That bit is so close to 0, you can treat it like it's 0 as long as you know it's not 0. And what you'll notice is you actually went back and you wrote down double signs. Now, for most of us, we don't even write double signs anymore. That we've actually worked our way through that and we just go, no, I'll just simplify everything to a single sign if I need to. So I'm going to argue to you, don't backtrack to grade 7 or grade 8. Avoid double signs. So when you take a look on top, this is actually what it is. If I am adding a negative, then really that means subtract. Okay, on the bottom, that really says take 3, subtract a negative number. Well, if I subtract negatives, then I really add. I'm going to argue that most people who continue to write down double signs seem to struggle. Let alone does it cause a second sign consideration, but it also makes your line look uglier. Like, look at that second red line versus the third red line. So, everything you see on that screen is correct. But I want to get rid of that, and I want to walk through the way that we can go straight to single signs. Okay. So, how would I think of this if I were you? Okay. I'm going to have to sub in huge negative values. That's what my limit tells me. So, I have nowhere to sub it in for that 1. Now, instead of blindly copying down that plus, I'm going to hold on for a second, and I am going to tie that plus to my numerator, because that is a positive 2 over x. And so really what I consider then is a positive 2 over my negative infinity. And so when I have a positive value divided by a negative value, then I'm going to have to subtract whatever that bit is, because it'll be a negative bit. And I know that 2 over a bigger and bigger number that always keeps getting bigger continues to get smaller and smaller and smaller and approaches 0. Now, how do I actually work my way through this? Take a look at the bottom. As I go to sub in on the bottom, I notice there's nowhere to sub in an x value in 3 because there's no x there. Now I'm going to look at the green circled fraction. I'm actually just going to look at 1 over x. And I say to myself, okay, Any fraction where the top is constant, the bottom gets bigger and bigger and bigger, will approach a value of 0. And now is where I tie in the sign of that numerator. That numerator is negative. It's a -1. And now, as I take that -1 and I divide it by a huge negative number, we can see that a negative divided by a negative really means that I'm going to add that bit. I want to get rid of the blue because we never ever write that down. And I want you to notice that that first line of my red now that I've evaluated, my 1 minus 0 over my 3 plus 0, is an awful lot more simplified because it doesn't have my double signs. Okay, here's where we come back to that rhyme a little bit. Those zeros are so close to 0 we can treat them like they're 0. So, treat them like they're 0. 1 minus 0 over 3 plus 0. However, we know that they're not really zeros, they're really bits. So we know that the value of our curve approaches a value of 1/3, but it never equals a value of 1/3 because the only way it could equal 1/3 is if these were zeros, and they're not, they're bits. So we never quite get to 1/3, telling us that as we go forever to the left, we actually have an asymptote at y equals 1/3. Now, there will be a little bit of concern over, but wait a second, if those aren't zeros, then they look like they're labeled as zeros right now, because they don't have their little directional symbol on top. They're not needed in this instance, because when you take a look, this is all happening within your limit. And so we know that in this instance, we are examining a value that we are approaching, but never touching. Okay. There's how we evaluate our end behavior. Now, we're going to leave a little bit in terms of the nature of the curve, and let's jump over to the other side and start to examine what's going to happen as we go forever to the right. So we have our limit as x approaches positive infinity. And just because this is still new for us, I'm going to write in that full manipulated version. Okay, how can we work our way through? Well, now we notice in this limit we have to imagine subbing in huge positive values for x. Okay, there is nowhere to sub in for x. And anytime I see a fraction where the top is constant and the bottom gets bigger and bigger and bigger, then I know that that value approaches 0. Now I have to consider, well, what sign is that bit? Because I know it's not really a 0, it's just a really small number. So I tie together the sign of my numerator, it's a positive, and now I also look back and remind myself that what I'm examining is subbing in huge positive values. So I have a positive divided by a positive. That makes that a positive bit. There we go. I'm just going to get rid of those blues and restate our positive. Okay, on my denominator, I have nowhere to sub in for x in 3, so there's my 3. And now I have a fraction where the top is constant, the bottom gets bigger and bigger and bigger, therefore it approaches a value of 0. Okay, I'm just going to get rid of those and restate my 0. Now I tie together the sign of that numerator. My numerator is negative. I remind myself that what I'm doing is I'm subbing in huge positive values, so my negative divided by my positive is a negative. Okay, I'm just going to get rid of those blues and restate my negative. Now I can just go through and evaluate. Those zeros are so close to 0, I can treat them like they're 0. But I know they're not really 0, and that's why I approach my asymptote at 1/3. Notice, I'm stating y equals 1/3 for two reasons. Number one, I'm finding a y value. Number two, it represents the equation of a horizontal line, and so it has to be y equals as my equation. Okay, there is us examining end behavior. Hopefully that's not that bad. And we can see that red process. However, what I'm going to say is we're maybe halfway. And maybe as we progress through this process, we may just be through the easy part. So what we're now going to examine is what is that curve doing as we go forever to the left and forever to the right. In order to do that, I'm just going to sneak in a little picture of a curve. And what we've just found is my asymptote would exist somewhere along y equals 1/3. So I hope that just by putting up that little picture, we can see that my curve would have to be above that red line or below that red line. We know it can never equal that red line as we go forever left, forever right. So what we need to do then when we examine end behavior is not only examine, well, what does that curve approach, but we also need to examine the nature of that curve, that being, does it approach from above or from below? So what we're going to do is we're going to go back and we're going to examine the left side limit, that forever left limit. And what we're going to do is we're going to take a look at our bits. So I want to go through really slowly here, really slowly, to make sure that we are good with this concept. To examine, should we be approaching from above or below, we always go back to at least that line that includes our bits. Okay, this is going to get really repetitive, and I apologize for the repetitiveness. However, it is needed. When we examine that line that I just checked off, the reason why we do is because my line can never equal 1/3, because the only way that it equals 1/3 was if those zeros actually equaled 0, and we know that they don't equal 0 because those fractions that they came from had numerators that were not 0. So that really represents 2 of some bit, and on the bottom 1 of some bit. Okay, I'm going to get rid of that green. We go back to that line with the check mark beside it, because that line is going to be the key to examining. Since we're never equal to 1/3, do we really have a value that's greater or one that's less than 1/3? We need to acknowledge that these bits are going to be what changes it from a value of 1/3. You see, there's my 1/3. But on top, my minus a bit, and on the bottom, my add a bit, they're going to change the value away from 1/3. So I have to examine the effect of what I've outlined in green, the effect of the bits. Okay. So now I need to go back to grade 4, and I mean literally back to grade 4, when we start to examine fractions and what fractions mean. So let's take a look at the top. What happens when we subtract a bit off the top of a fraction? So the question we're really saying is, what happens to the value of a fraction when we subtract a little bit off the top? I would hope that when we see that subtract a little bit off the top, we notice that that means the fraction value drops. Okay, I'm hoping we can see that, but for us, it's important for us to remind ourselves that the top of a fraction always represents the number of pieces. Like, I hope that we don't have to go back to drawing like a pizza and dividing it up into slices to examine the nature of a fraction. However, it's important for us to note that the top of the fraction always tells us how many of something has. It has our quantity, the number of pieces. And so, if we take a little bit off the top, then we have fewer pieces. And if we have fewer pieces of something, then the number or the overall value goes down. Okay, that's not the only component, though, that determines the value. On my denominator, it's not really 3. It's really 3 plus a bit. So what does the effect of adding a little bit to the bottom do? Well, I'm hoping that when we notice that if that bottom isn't really 3, but it's really 3 and a bit, a number a little bit bigger than 3, then if I have a number that is a little bit bigger than 3 on the bottom, then that is going to give me a lower value. I hope that we can recall that what the bottom of my fraction determines is the size of the bit. It's the size of the pieces. This one might be something where we have to go back and we have to say, okay, we're going to draw our pizza. Clearly, if I had a pizza that was broken into thirds, and now I add a little bit to the bottom, so imagine it was like fourths, that by me making my denominator a larger value, I'm making the size of each piece smaller. And so if the size of each piece becomes smaller, then I have a smaller value, all other things being constant. So now I want you to take a look back at those 2 arrows that I drew in my first limit. The top subtract 0 caused the fraction value to be a little bit less. The bottoms plus a bit caused my fraction to be a little bit less. Both of those have an effect that my value is a little bit less. And so I'm going to draw my conclusion. So what I have then is a lesser value. It's really less than 1/3. And if I asked you, well, where are things less than 1/3, relative 1/3, we could then draw the conclusion that we are below. What I actually just found out on that limit, as I go forever to the left, my function value is always a little bit less than 1/3. That's why we can state that we approach from below. Okay, that's not always an easy concept. I want to walk through the other limit because if we have a little bit of confusion with it, I think if we give it another go, we can see some more stuff in practice and it'll help us to deepen our understanding. But again, every time we revisit something, I want to remind you, we're just talking about grade 4 fractions. What is the meaning of a fraction? So when you face some confusion, don't go to something difficult, something recent. Go back to the basics. Okay, I've just shrunk that down a little bit so we have a little bit more room to the right. Okay, we are going to examine my top bit. So what is the effect of adding a little bit to the top? Okay, I know that my top represents the number of pieces. So if I add a little bit to the top, then that means I have more pieces. More pieces means the value of my fraction is a little bit bigger. Okay, what about the value of that bit on the bottom? Well, if I subtract a little bit off the bottom, then that means I'm dividing by a smaller value. And in fractions, if I divide something by a smaller value, that means I have bigger pieces. Bigger pieces means I have more. So if I look at the effect of both those arrows, my top adding on a bit meant my fraction value was bigger. My bottom subtracting off a bit meant my fraction's value was bigger. Both of those things mean that I have a value that is more, or larger, or bigger. And if I'm really more than 1/3, then therefore, where are values more than 1/3, relative 1/3? They are above. And so what I just found then is that the value of my fraction never gets to 1/3, it's always a little bit bigger. And therefore my curve would approach from above. There you go. There is the process for us examining end behavior of a curve. The thing to keep in mind, it's only grade 4 fractions. So as we start to consider that, again, think basic, don't think current. Okay, we're going to jump through and we're going to deal with a few more examples. We're going to pick up the pace now. Again, it's going to get repetitive, but we're trying to drill in a thought process as we work through this. Okay, let's keep it going. Okay, we take a look at the function given in B. F of x equals 5x squared minus 3 over x plus 5. We now have to examine, if we have a horizontal asymptote, where does it exist? Okay, so we're going to examine end behavior. So the first thing we want to do is we want to manipulate the way that looks. Now, I'm just going to write some stuff down. Please don't copy this down. But this would be the work we would be doing. We need to divide top and bottom both by the largest power of x. So a lot of people will then want to write this down. Maybe, for right now, we recognize that the largest power of x is x squared, and so I need to divide every term by x squared. I'm hoping, though, that you can look at that process and you can jump straight to a simplified form. So I'm even so confident that you could rewind it and look at that green if you needed to be, but we're going to erase all that. And we're going to jump straight to a blue. Okay, divide every term by x squared. My x squareds divide out. Nothing to divide out. One of my x's will divide out. Nothing divides out. And we come right in on that blue. Now, I am so confident that you guys will get so used to that you won't even do that as a separate step. So you can rewind back to this point if you need to, but I'm going to erase all of that because we know to examine end behavior means that I need to examine my limit as x goes forever to the left of that function. And so why not just divide out your largest power of x on your very first line within your limit? So divide 5x squared by x squared, divide 3 by x squared, divide x by x squared, and divide 5 by x squared. And we just write it in on the first line. That's going to save you guys some time. Especially when you get practice, you're going to get really good at that. Okay, now I'm going to go through and I'm going to evaluate that. So I'm going to sub in huge negative numbers. That's what my limit tells me. Huge negative numbers. Okay, there's nowhere to sub it in for the 5, so that's a 5. My fraction 3 over x squared is going to approach 0. Now when I tie that together, I have a negative 3 divided by a really big number, but because I'm going to square the x values I'm subbing in, my denominator will always be positive. So I'm going to have a negative divided by a positive. That is a negative. Okay, I'm just going to get rid of all that blue, replace my negative. Now I take a look at my denominator. Okay, my first term is a fraction where the top is constant and the bottom gets bigger and bigger and bigger. That approaches 0. What sign would that be? Well, I have a positive 1 over a really big negative number, so a negative. My second fraction, well, my top, that will approach 0. My top is a positive 5. My bottom will always be a positive value. And so a positive divided by a positive is a positive. And there we go. Okay, now we're at the easy part. Those are so close to 0, we treat them like they're 0. But then we need to remember that they're not really 0. Okay, let's take a look at that denominator, because my denominator right now says that it's 0, but we know it's not 0. So we have to figure out, well, what sign bit is it? And for us to examine that, then we have to go back and see where that 0 came from. And so that was a 0 plus a 0. Now, we can even notice that what that says is it's a negative number plus something else. And if I was to ask you, if you have a negative number added on to a number, does that give you a positive or a negative number? I would hope our answer would be it depends. Right? -3 added on to 2 is a different sign than -2 added on to 3. The size of those bits matter. So we need to go back and we need to kind of figure out, like, well, how big are those bits? Okay. I'm going to now erase that because for us to examine that, we have to look back up at that gold. And we now need to consider this bit that was negative came from a 1 over x. This bit that was positive came from a 5 over x squared. We need to kind of consider, like, how do they compare to each other? Which one's bigger, which one's smaller? Because if we know which one's bigger and which one's smaller, then when we add those bits together, we can figure out what sign we get. Okay. I actually want you to pause the video pretty soon because I want you to go on record in your mind. I want you to try to consider which one of those bits is bigger. What's bigger, 1 over x or 5 over x squared? Okay, I want you to pause the video now and come up with an answer to that. Okay, we're back. Now, this is probably answer to this question is going to be a little surprising to you. And if we were in class right now going through this live, I would actually expect an awful lot of people to tell me 5 over x squared was larger. They would be incorrect. But I would expect that from a lot of people for 2 reasons. Okay, first off, take a look at your numerators. Like, I would expect a lot of people to look at the numerators and maybe say, the first one is 1 of something, the second one is 5 of something. 5 is bigger than 1. So I'm going to choose the second. Now, I hope that that would be a very short-sighted argument, and we would recognize the short-sightedness of that, and we would say, yeah, but it depends on what size bits. So then we go through and we examine the denominator. And somebody might say, yeah, but like the first one's a divide by x, the second one's a divide by x squared. X squareds are larger than x's, and so the second fraction is larger. And then that's when I'm going to stop you and I'm going to say, but you ignored where the x squared was. Yes, I would agree that x's are smaller than x squareds for most values. At least most values we consider. However, we have to make a note of where they are. Notice that they're on the denominator. So just even in this instance, I want you to imagine that your x was a value of 100. That means that that first fraction is 1/100th. Your second fraction is 5 over 100 squared. That's 5/10,000ths. So if I was to say to you then, which one of those fractions is larger? 1/10 or 5/10,000ths? Remember what we're looking at here. We're looking at what is happening to x as it becomes huge. So when a value happens to be small, like we're not really considering this. We're considering only for huge x values. And then for some people, they might ask, like, well, what's the barrier between small and large? And I'm going to say, like, there isn't really one. It's just that x is getting larger and larger and larger. Like perhaps 1 million is small. But if you take a look at that denominator, can you imagine? This would be 1/1,000,000th. My other denominator would be 1 million squared. So I'm hoping that we can look right back to those bits and we can see that because that denominator is squared, this second fraction will always be smaller than the first fraction if we allow x to be really, really big. Okay, come back to that screen if you need to, but I'm going to erase all that stuff because we got to jump back into our limit. So, as we take a peek then, back up into our original, we are now comparing 1 over x to 5 over x squared. And we see that 1 over x is a larger amount. Okay, that 1 over x is the larger amount. That tells me that on the next line, this negative bit is a larger value than the positive bit. Now, I want to be very clear here for anybody who's kind of confused of, no, but wait a second, I thought negative amounts were always less than positive amounts. I'm not talking about the sign of that. I'm talking about its magnitude, just the number. That negative bit, the number of it, will be a larger number than the positive bit. And because that bit is larger, then I would actually have an instance like we had before of where I would have a number like -3 add on 2. My negative number is larger than my positive number, and so when I combine them, I'm always going to get a negative number. Okay, I'm going to erase all of that because that then tells me this bottom should always be a negative bit. Okay, then what do we find in that instance? Well, we find that we have 5 divided by a really small number that's always getting smaller, so that's going to give us a big value. And the top is a positive and the bottom is a negative, so a positive divided by a negative is a negative. Now, I just want to stop there for a second, and I want us to notice that what we actually just found was that we have no horizontal asymptote. Because look what happens when we go forever to the left. My curve doesn't approach a value. It goes to negative infinity. And so if I was to create a graph for this, then when I go forever to the left, that just says that my curve has to go down. Now, I don't even think that we have to go through this process then to examine what happens when we go forever to the right. We actually just found out something, that we can go through this process to examine end behavior and discover that certain functions don't have horizontal asymptotes. Now, we just covered a ton of material, and by no means do I think that we are anywhere close to being automatic with this. But I do want to sum up some stuff that we just found. Okay, we're going to sum up some stuff. If you need to rewind a little bit at any point during this slide, this screen, then feel free to rewind to look back at what we encountered. Because what we just noticed in the last example that we did was that we had no horizontal asymptote. And what was different about that function? Well, you'll notice that the degree that we had on top was larger than the degree we had on the bottom. And so when you went through your process to divide by the largest power of x, if the largest power of x is on top and not on the bottom, then at some point we're going to have fractions on the bottom that still have something over x, or something over x squared, or something over x cubed, or so on. And all of those fractions always approach 0 when we allow x to get bigger and bigger. That means that we will always have divide by zeros. And I can't divide by 0 and get a constant, which means I'm always addressing an instance where I'm going forever up or forever down. Okay, the previous example in A, though, we did get to a horizontal asymptote, 1 at y equals 1/3. So what can we learn through just those two examples and then the reasoning you see in red? That for me to find a horizontal asymptote, or I guess better stated, for a horizontal asymptote to exist on a curve, the degree of the expression on the numerator must be equal to or less than the degree on the denominator. Now, that can get a little wordy, and so I think the best way to think about it then is your highest power of x must be on the bottom. So imagine we had a function that was like f of x equals x plus 3 over x squared plus 5x. If you answer the blue, that'll tell you whether there is a horizontal asymptote or not. Is the highest power of x on the bottom? Your answer is yes. Therefore, there is a horizontal asymptote. If I was to give you this, x plus 3 over 5x plus 2, answer the blue. The highest power of x must be on the bottom. Is the highest power of x on the bottom? Your answer is yes. The fact that it's on both the top and the bottom, we don't care. Is it on the bottom? Yes. Therefore, you do have a horizontal asymptote. But the second I go and I do this, and I put your highest power of x on the numerator, then all of a sudden, we should know we will not have a horizontal asymptote. Okay, you come back to this screen anytime you need it. But now what we're going to do is we're going to jump in and we're going to work our way through actual curve sketching dealing with horizontal asymptotes. So, I want you to take a look at the problem. We're going to actually go through a big complex problem right now. We're going to find all the vertical and horizontal asymptotes, and then we're going to actually sketch that graph. We're going to do a formal sketch. Okay. I want to take you through the full process. By no means do I think that horizontal asymptotes are automatic, not at all. However, I would hope that vertical asymptotes would be getting pretty close to being automatic. So, you are going to follow along with me. I want you to pause when you need to, pause when I tell you to, but we're going to go through the full process of doing some curve sketching. So, let's take a look at 2. Okay, we need to sketch that curve. So, the first thing we do is we always try to simplify our graph. So, I notice that I can factor my top and factor my bottom. And when I do that, my x plus 1's divide out, and that whole function simplifies to that. That is the simplified version that I want to use. Now, we also don't forget that that division by that factor of x plus 1 meant that we have a gap, and we know that there's a gap at x equals negative 1. Now, you could go through and you could find that value, and a lot of people will like to right away, that they're going to sub negative 1 into our simplified form. They would then get 4 on top, negative 2 on the bottom, 4 divided by negative 2, negative 2. There's the location of our gap. Okay, now what we're going to do is we're going to go through and we're going to find our vertical asymptotes. So this is going to be an opportunity for you to see, do you have what you need from that vertical asymptotes lesson? Okay, we're going to hop onto the next screen and we're going to go through and find vertical asymptotes. So what you see on the screen then is the simplified equation for us. Okay, we should know then that we have a vertical asymptote at x equals 1. That's what makes my denominator equal to 0. And so we are now going to examine the limit as x approaches 1 from the left in x plus 5 over x minus 1. And we're going to examine the limit as x approaches 1 from the right. And I'm just going to save some time and write in my f of x. Okay, what I want you to do is I want you to pause the video now, and I want you to go through and find what those limits work out to be, your nature of your curve. Okay, pause it now. Okay, so we're back. So let's examine that left side limit. Okay, we're going to sub in values so close to 1 we can treat it like it's 1. But then we have to remember it's not really 1. it's now going to be a value a little bit less than 1. And so if I look at my denominator, a little bit less than 1 subtract 1 means that denominator is going to be a negative value. And so if I have 6 divided by a really small number that's always getting smaller, then I'm going to get a huge value. And if I have a positive divided by a negative, then I approach negative infinity. Okay, now I examine my right side limit. So I can look back to my original function to see my substitution into the top of 1 is 6, my bottom is 0. Now I remember that's not really a 0. I'm subbing in a value a little bit bigger than 1. So if I take something that's a little bit bigger than 1 and then I subtract 1 from it, it's always going to be a positive value. And so my positive divided by my positive is positive, and 6 divided by a really small number always getting smaller, infinity. So hopefully our limits for our vertical asymptotes check out. And now what we're going to do is we're going to walk through our horizontal. Okay, why do I know that I have a horizontal right now? Look at the white function. What is my highest power of x? It's just an x, or x to the exponent 1. Does x to the exponent 1 exist on my denominator? Yes. Therefore, I have a horizontal asymptote. So let's go through and let's examine our horizontal asymptote. Okay, I'm going to examine the limit as x approaches negative infinity, and I'm going to divide top and bottom both by the largest power of x. So x divided by x, 5 divided by x divided by x, 1 divided by x. Okay, this is me finding my horizontal asymptote. Now, if you're feeling pretty confident, even if not, what I want you to do is I want you to work your way through and try to come up with what is the horizontal asymptote and what is the nature of the curve. What is our end behavior? Okay, pause it now. Okay, we're back. So my expectation would be confidence level still probably really low. That's okay. That's where we should be. Okay, now we're going to work our way through. So I'm imagining subbing in huge negative numbers. Well, there's nowhere to sub it in for the 1. My fraction 5 over x is going to approach 0. And on the bottom, there's nowhere to sub it in for 1. And my 1 over x is going to approach 0. Okay, now I need to know what are the signs of those fractions, those bits. So on the top, I'm going to have a positive 5 divided by a negative number. So my positive divided by a negative is a negative. And on the denominator, I'm going to have a negative 1 divided by a really big negative value. So a negative divided by a negative is a positive. Okay, well, we can calculate that then, and we know that 1 divided by 1 equals 1. Okay, but we know that it's not really 1, because it would only be 1 if those were really 0, and we know that they're not 0, they're really bits. So now we need to examine our end behavior, the nature of that curve. Okay, let's take a look at those bits then. On the top, 1 minus 0, I am subtracting off a bit. So what happens if I subtract a little bit off the top of a fraction? My fraction value becomes smaller, which means I have fewer pieces, which means I have a lower value. Okay, let's take a look on the bottom. I have 1 plus a bit. Well, if I add a little bit to the bottom, then I make the bottom's number bigger. And if I divide by a bigger number, then I make a smaller value. Well, the effect then is the top makes it smaller and the bottom makes it smaller. Therefore, I have a smaller amount. And it's okay, like you can write like smaller. Like we have a smaller number. Or we have less. And where are values that are smaller than 1? They are below. There we go. So hopefully that matched up. And we're starting to feel a little more confident to then be able to work our way through and address our other limit. So we can go forever right. Some people are going to be so confident that they're going to write in f of x here to save time and just look back at what we're subbing in. For others, we are not there yet, and that is okay. And we're going to write in that manipulated form of our function so we can explicitly see what we're subbing in. Okay, I want you to pause the video now and evaluate that limit. Okay, we're back. So we can work our way through. I'm imagining subbing in huge values for x. Well, there's nowhere to sub it in for that 1. That fraction is going to approach 0. Nowhere to sub it in for that 1. And that fraction approaches 0. Okay, now I'm looking on top. I have a positive 5 divided by a really big positive number. So that's going to approach a positive bit. On the denominator, I have a negative 1 divided by a really big number. That will give me a negative bit. And we can do the same thing, but I think we should be able to just jump straight to 1. Okay, now we have to examine nature of the curve. Okay, so let's examine our bits. We're going to look at the top. I have 1 plus 0, 1 plus a bit. So if I add a little bit to the top of a fraction, then I make that fraction's value bigger because I have more pieces. If I subtract a little bit off the bottom, then I am dividing by a smaller value. That means I have bigger pieces, so I have more, a bigger value. Well, the top effect made it bigger, the bottom effect made it bigger, therefore I have a larger value. And where are values that are larger than 1? Above. Okay, now it's time to go through and sketch that function. Okay, we're going to take all the information we found and we're going to produce a picture. Here we go. Okay, so what you see on the screen then are all the values and properties that we found. And so what I'm going to do then is I'm going to take all of those properties and we're going to combine them all to produce a sketch. Okay, here we go. First thing I want to do is I want to go through and I want to put on my asymptotes. My vertical asymptotes are going to act like a wall that are going to allow me to kind of break up my graph. So I'm going to imagine what 1 is on my x-axis, and I am then going to go through and say that would then be my asymptote at x equals 1. I know my nature of my curve says as I approach from the left, I'm going down, and as I approach from the right, I'm going up. Now I can go ahead and I can put on my horizontal asymptote. So that's going to be my y equals 1. Now you'll also notice that I never had to explicitly state that. Well, it's because the question itself never asked me state what the horizontal asymptote was. If the question had said, find the horizontal asymptote, then I'd have to state it explicitly. In this case, I'm just curve sketching. If it was, then I would require that we wrote y equals 1 as our solution. Okay, I found that as I went forever to the left, I'm approaching from below, and forever to the right, I'm approaching from above. Well, we also know that we have a gap at -1, -2. So if I was to try to piece that together a little bit, then I might be like at -1, -2, somewhere down here. Okay, we have the ability to now put together all of that information to produce a sketch. And so I'm going to put all of that together to produce a gold sketch. Well, let's look up in the top right corner, because I think because we have rising to the right, or sorry, from the right side rising and approaching from above, we can put that together to create a smooth curve. So I could then curve that gold and produce that. Nice, that's not too bad. Now you take a look to the left, and I want to make sure that we don't think that this curve has to get this close or this close to those asymptotes in those positions. That's just where our curve approaches. So if I needed to piece all of this together, then I could say that I was going through that gap that you see at -1, -2. I'm now going to draw that as a gap. So I've got a little opening at -1, -2. And now I can approach that asymptote going down and approach my horizontal asymptote from below, and we get something that looks like that. That gold sketch with the green gap, along with our asymptotes, is a pretty good sketch. And there is our curve sketching process. So, I know we've only done a few examples, but there is a ton of theory in here. Your job is to try to drill in, how do we find horizontal asymptotes? And then if we can work towards a comfort level to be able to combine everything into a sketch, then I think we're doing really well. Really well. Okay, your job now, jump in and get as much practice as you can. Good luck.